In the last lecture, we have seen that how one can obtain UMA confidence interval by inverting the acceptance region of the UMP test. But the problem is that in most of the cases, UMP test does not exist for two-sided alternatives. Therefore, the UMA intervals are usually of the form -infinity, C or C to infinity. To overcome this problem, in this lecture, we shall discuss the idea of uniformly most accurate unbiased confidence intervals. These confidence intervals can be obtained by inverting the acceptance region of the uniformly most powerful unbiased tests. We shall also discuss a very important result relating to the expected length of the confidence interval with the average probability of false coverage. Some examples are discussed in this connection. In the last lecture, we have studied test inversion as one of the methods of constructing confidence intervals. We showed that UMP tests lead to UMA confidence intervals. In module 32, we have seen that UMP tests generally do not exist for two-sided alternatives. In such situations, we either restrict consideration to smaller subclass of tests by requiring that the test functions have some desirable properties, or we restrict the class of all alternatives to those near the null parameter values. The construction of unbiased tests and locally most powerful tests were already discussed. In this lecture, we discuss how the concept of unbiasedness can be used in constructing confidence intervals. First, we define unbiased confidence set, a family of confidence sets capital Sx, where x belongs to script x, for a parameter theta is said to be unbiased at confidence level 1 minus alpha if probability under theta belongs to Sx is greater than equals to 1 minus alpha for all theta belongs to script theta, and probability under theta dash belongs to Sx is less than equals to 1 minus alpha for all theta not equals to theta dash. If Sx is an interval satisfying 1 and 2, we call it a 1 minus alpha level unbiased confidence interval. Now we define uniformly most accurate unbiased, that is UMAU confidence set. A family of confidence sets capital S naught x, where x belongs to script x, for a parameter theta is said to constitute a family of UMAU confidence sets of confidence level 1 minus alpha if it is unbiased at confidence level 1 minus alpha, and probability under theta dash belongs to S naught is less than equals to probability under theta dash belongs to Sx for all theta not equals to theta naught, and for all S satisfying the above conditions 1 and 2. Thus, a family Sx of confidence sets for a parameter theta is unbiased at level 1 minus alpha if the probability of true coverage is at least 1 minus alpha and that of false coverage is at most 1 minus alpha. In other words, Sx traps a true parameter value more often than it does a false one. Now we consider the following result. Let for each theta naught belongs to script theta, capital A naught theta naught be the acceptance region for a UMP U level alpha test for testing H theta equals to theta naught versus HA theta not equals to theta naught. then the set S naught, which is equals to the set of all theta such that X belongs to capital A naught, is UMAU at confidence level 1 minus alpha. Now we consider a proof of this result. To see that capital S naught is unbiased, we note that since capital A naught is the acceptance region of an unbiased test, probability under theta, theta dash belongs to S naught is equals to probability under theta X belongs to A naught bracket theta dash is less than equals to 1 minus alpha. We next show that S naught X is UMA. Let Sx be any other unbiased 1 minus alpha level family of confidence sets, and we write A theta equals to set of all x such that theta belongs to Sx. Then probability under theta X belongs to A theta dash is equals to probability under theta, theta dash belongs to Sx is less than equals to 1 minus alpha, and it follows that A theta is the acceptance region of an unbiased psi alpha test. Hence, probability under theta, theta dash belongs to Sx is equals to probability under theta X belongs to A theta dash for all theta belongs to script theta, and it is greater than equals to probability under theta X belongs to A naught for all theta greater than equal to theta naught, and which is equals to probability under theta, theta dash belongs to Sx for all theta not equal to theta naught. And the last inequality follows since capital A naught is the acceptance region of a UMPU test. This completes the proof. Now we consider some examples. Example 1. Let x1, x2, xn be a random sample of size n from normal distribution with mean theta and variance 1. The rejection region for a UMPU size alpha test for testing h0 theta equals to theta naught versus h1 theta not equals to theta naught is given by modulus of root n into x bar minus theta naught is greater than tau alpha by 2, where tau alpha is the upper 100 into alpha percent point of standard normal distribution. And we define the acceptance region as capital A theta naught equals to set of all x such that theta naught minus tau alpha by 2 divided by root n less than equals to x bar less than equals to theta naught plus tau alpha by 2 divided by root n. And therefore Sx equals to set of all x such that x bar minus tau alpha by 2 divided by root n less than equal to theta less than equal to x bar plus tau alpha by 2 root n. Hence the UMAU confidence interval is given by the interval x bar minus tau alpha by 2 divided by root n to x bar plus tau alpha by 2 divided by root n. We consider the second example. Let x1, x2, xn be a random sample of size n from normal mu sigma square population where both mu and sigma square are unknown. The rejection region for a UMPU size alpha test for testing h0 mu equals to mu naught versus h1 mu not equals to mu naught is given by modulus of root n into x bar minus mu naught is greater than s into Tn minus 1 comma alpha by 2, where s denotes the sample standard deviation. Therefore s square equals to 1 by n minus 1 summation over I from 1 to n xi minus x bar square, and Tn minus 1 comma alpha is the upper 100 into alpha percent point of a t distribution with n minus 1 degrees of freedom. And therefore we define the acceptance region capital A theta naught equals to set of all x such that mu naught minus s by root n into Tn minus 1 comma alpha by 2 less than equals to x bar less than equals to mu naught plus s by root n into Tn minus 1 comma alpha by 2. And therefore Sx is equals to set of all x such that x bar minus s into t alpha by 2 divided by root n less than equals to theta less than equals to x bar plus S into T alpha by 2 divided by root n, and hence the UMAU confidence interval for theta is given by the interval x bar minus S into T alpha by 2 divided by root n, comma x bar plus S into T alpha by 2 divided by root n. We consider our third example. Let x1, x2, xn be a random sample of size n from normal population with mean theta and variance sigma square, where theta and sigma square are both unknown. The UMPU test for testing H naught sigma equal to sigma naught versus HA sigma not equal to sigma naught is given by psi V is equals to 1 if V by sigma naught square less than C1 or V by sigma naught square greater than C2 equal to 0 otherwise, where V equals to summation I from 1 to n xi minus x bar square. Therefore, under H naught V by sigma naught square follows chi square n minus 1, and hence the acceptance region for the UMPU test is the region C1 less than equals to summation xi minus x bar square by sigma naught square less than equal to C2, where C1 and C2 are obtained from the following conditions: expectation under sigma naught square psi V is equals to alpha, and expectation under sigma naught square V into psi V is equals to alpha into expectation under sigma naught square psi V. By inverting the acceptance region of the UMAU confidence interval for sigma square is given by the interval summation I from 1 to n xi minus x bar square divided by C2, comma summation I from 1 to n xi minus x bar square divided by C1. We consider our fourth example. Here we consider two samples. Let x is the first sample, x equals to x1, x2, xm. It is drawn from a normal theta sigma square population, and y is our second sample. It is actually y1, y2, yn. It is drawn from the normal mu sigma square population. The samples are drawn independently of each other. Consider the parameter of difference of means. Let delta equal to theta minus mu. The acceptance region for a UMPU test for testing H naught delta equals to delta naught versus H1 delta not equals to delta naught is given by capital A theta naught is equals to set of all x such that x bar minus S into within root over 1 by m plus 1 by n into t m plus n minus 2 comma alpha by 2 less than equals to delta naught less than equals to x bar plus S into within root over 1 by m plus 1 by n into t m plus n minus 2 comma alpha by 2. This is actually the Fisher's t-test, where S square is the pooled sample variance, which is equals to summation over I from 1 to n xi minus x bar square plus summation over I from 1 to n yi minus y bar square whole divided by m plus n minus 2. And therefore we get Sx equals to set of all x such that x bar minus S into within root over 1 by m plus 1 by n into t m plus n minus 2 comma alpha by 2 less than equal to delta less than equals to x bar plus S into within root over 1 by m plus 1 by n into t m plus n minus 2 comma alpha by 2. Hence, the UMAU confidence interval for delta is given by the interval x bar minus S into within root over 1 by m plus 1 by n into t m plus n minus 2 comma alpha by 2 comma x bar plus S into within root over 1 by m plus 1 by n into t m plus n minus 2 comma alpha by 2. Now we discuss a important relationship between shortest length confidence set and the UMA confidence set. If the measure of precision of a confidence interval is its expected length, one is naturally led to a consideration of unbiased confidence intervals. Pratt has shown that the expected length of a confidence interval is the average of false coverage probabilities. We consider the following result. Let script theta be an interval on the real line and P x comma theta be the PDF of x. Let capital Sx be a family of 1 minus alpha level confidence intervals of finite length. If the length of a confidence set Sx is lambda of Sx, which is the Lebesgue measure of the set Sx, then expectation of lambda under theta is equals to integral over theta dash not equals to theta, probability under theta, theta dash belongs to Sx d theta dash. We consider a proof of this result. Lambda Sx is equals to integral over theta dash belongs to Sx d theta dash, and therefore expectation under theta lambda Sx is equals to integral lambda Sx into px theta dx, which is the double integral as integral over theta dash belongs to Sx d theta dash into px theta dx. Now, by Fubini's theorem, we interchange the order of the integral and we get integral over theta dash belongs to Sx px theta dx d theta dash. The inner integral is actually the probability of theta dash belongs to Sx, and therefore we get integral probability of theta dash belongs to Sx d theta dash, which is equals to integral over theta dash not equals to theta, probability theta dash belongs to Sx d theta dash. Thus we have seen that if Sx be a UMA confidence interval, then it is also the uniformly shortest expected length USEL confidence interval. Similarly, UMAU confidence interval is equivalent to the uniformly shortest expected length USUEL confidence interval. Now, we are going to discuss the idea of randomized confidence set. The idea of inverting acceptance region to obtain the confidence set cannot be directly used for discrete case, since we have randomized test. In fact, in discrete problems, inverting acceptance region of randomized tests may not be lead to a confidence set with a given confidence coefficient. Note that randomization is used in hypothesis testing to obtain tests with a given size. Thus, the same idea can be applied to confidence sets, that is, we may consider randomized confidence sets. Suppose a UMPU test for testing H0 or H colon theta equals to theta naught versus HA theta not equals to theta naught is given by psi theta naught x is equals to 1 if T1 greater than some constant C2 which depends on T2 and theta naught, or T1 less than some constant C1 which depends on T2 comma theta naught, equals to gamma 1 if T1 equals to C1 equals to gamma 2 if T1 equals to C2 and is equals to 0 if T1 lies between C1 and C2. Let capital U be a random variable that is independent of x and has the uniform distribution rectangular 0 1. Then the test psi curl theta naught x comma u, which is actually the product of the indicator function I u comma 1 and psi theta naught, has the same power as psi theta naught and is non-randomized if u is viewed as a part of the sample. Let capital AU theta naught equals to set of all x comma u such that u greater than equals to psi theta naught x be the acceptance region for psi curl theta naught x comma u. If psi theta naught x has same size alpha for all theta naught, then inverting AU theta naught we obtain a confidence set Cx comma u is equals to set of all theta such that x comma u belongs to AU theta. We consider our last example. Let x and y are independently distributed as the Poisson distribution, Poisson lambda 1 and Poisson lambda 2. And suppose that we are interested in finding a confidence interval for the ratio rho equals to lambda 1 by lambda 2. Define T1 equals to x and T2 equals to x plus y. We know that T1 given T2 follows binomial T2 comma rho by 1 plus rho. A UMPU test for testing H naught rho equal to rho naught versus A rho naught equals to rho naught is given by psi theta naught T1 comma T2 is equals to 1 if T1 greater than some C2 which depends on T2 and rho naught, or T1 less than some C1 which depends on T2 and rho naught, equals to gamma 1 if T1 equal to C1, equals to gamma 2 if T1 equal to C2, and equal to 0 if T1 lies between C1 and C2. The acceptance region for non-randomized test is AU rho naught is equals to the set of all T1 T2 U such that U greater than equals to psi theta naught T1 comma T2, and the confidence set is given by C T1 T2 comma U is equals to set of all theta such that T1 T2 U belongs to AU rho. In this lecture we have seen that in case of uniformly most accurate unbiased confidence interval of level alpha, it covers the true value with probability at least 1 minus alpha, and it covers the false value with probability at most 1 minus alpha. We have seen that the uniformly most accurate confidence interval is equivalent to the uniformly shortest expected length confidence intervals, and the uniformly most accurate unbiased confidence intervals is equivalent to the uniformly shortest expected length confidence intervals.